Welcome back to ECE 442-542. This is our beginning of the marathon session. I'm not sure how many people we will have remaining at the beginning or the end of the second half, but we'll see. The plan is to record that, but I'm sort of shuffling these announcements. We will have a review session for exam number 1 this evening at 7 o'clock. Just if you do exit, make sure somebody is aware of your exit if you want to come back. The building may be locked at 7, and you may have to exit the building to use the restroom. So make sure we're aware that you're down there before 7 so you can get back in. Reading assignment, this particular lecture is dealing with material that is not explicitly on exam number 1. We are beginning unit 3 in this lecture, and obviously that means that we've now moved into chapter 4 of the notes for discrete time system foundations. That's not obvious, but we're now doing inverse Z transforms. If you're still needing help with homework number 2, which is due this evening, is you might look on D2L. There are some notes right below the assignment itself to try to help you with the block diagram state space material, and we'll actually go through hopefully some of that in the review session tonight, maybe some different ways of creating block diagrams or all delay block diagrams, state space, etc. There's also an additional lecture/video 2.1a that wasn't in class, but it's right below lecture video 2.1 that explains or tries to explain the Z transform of an exponentially damped cosine. Hopefully you can see the connection with the exponentially damped sine in problem number 4 of homework number 2. And finally, just in general, if you're searching or trying to find some help with some problems, I've tried to create discussion sections in each of the different units on the discussion page of D2L, and several students, and usually online students, are asking questions there, and sometimes they answer each other's questions, which is good. That's what I want. And sometimes I sort of introduce some of my thoughts on those questions as well. So you might look through those discussion posts if that might help you better understand some of the material that is being a part of that particular unit. In 1 week from today, we will have our first exam in this class on the 19th of February. As I said before, today what we want to do in this lecture is look at the inverse Z transform. And that's going to be in Unit 3. And Unit 3 and 4 material will not be on Exam 1. That will be on Exam 2. Hopefully that's all clear. But today we will talk a little bit more about region of convergence and how we might have different regions of convergence depending on when these sequences in the time domain are defined. Are they defined for n greater than or equal to 0, for little n less than 0, on both sides of 0? That then leads to different region of convergence patterns. On exam number 1, most of the stuff that we will deal with deals with the first pattern. The region of convergence is, for exam number 1, usually it's beyond some region or disk in the Z-plane. But today we're going to look at the different regions. We'll have all of the Z-plane with a disk removed from the center. We'll look at another region of convergence that is just a disk, nothing outside of it, and then we'll look at a donut or an annular shaped region of convergence. Those are our 3 regions, and we'll try to provide a broad overview of those patterns and then work through some examples. These region of convergences are really dealing with the definition of the Z transform. What values of Z allow this infinite series to sum to a finite value? What values of Z allow this sum to remain finite? That's what's governing the region of convergences. And I like to, if I'm thinking or trying to figure out what is my region of convergence, I just write this generic formula down, and then I examine what is the result of when these terms in this expansion are true or not, and what does that say about the values of Z that cause this expansion to be bounded or finite. With that said, let's now look at the topic of region of convergence, and here's the big picture is what we're going to be thinking about today. What are the main patterns? And then we'll have some variations on those patterns. But in general, we have three patterns. A large region of convergence with a disk removed from the center. That's pattern 1. A disk itself, that's pattern 2. And something sort of in between those is a donut or an annular shape. That's pattern number 3. And then we'll have variations on pattern 1 and pattern 2. Here's what I hope that you take from this first paragraph, is the region of convergence is separate from whether or not the sequence in time is bounded or unbounded. And we will actually talk about an unbounded region of convergence. That's not the same as an unbounded sequence in time. When I say an unbounded sequence in time, do you see these numbers just growing either as you go to the right as n increases or as you go to the left as n increases? The sequence values are going unbounded. When I speak of the region of convergence going unbounded, now I'm talking about this z-plane extending off to infinity. That's when the region of convergence is unbounded. And that's completely separate from whether the sequence of time in this class, it's usually a time that little n represents. This sequence of numbers in the time domain going unbounded is completely separate from the region of convergence. And that's what I'm trying to say here. The region of convergence is determined independent of any stability, if that's how you want to think of that time sequence. Is it stable or not? Is it bounded or unbounded? Versus whether the region of the region of convergence looks like. However, they are connected. If a signal is bounded, or the system whose pulse response is bounded, that's what I'm meaning by a system is stable, if the region of convergence contains the unit circle. You'll now draw this region of convergence, and if the unit circle is contained on top of, or it's kind of maybe difficult to describe, but I think you can understand the picture. If you now have this region of convergence and the unit circle is on top of that region of convergence, your sequence will be bounded. One fact that you also want to keep in mind relative to region of convergence is that if you have poles, they never are inside the region of convergence. They are always outside of the region of convergence. And outside could mean different things, but they are not lying on top of region of convergence, or the region of convergence does not contain poles. So the fact is, poles never lie on the region of convergence. Let's now talk about these patterns. Here's pattern number 1. And the important thing to pay attention to is, okay, this is the z-plane. This is the complex z-plane. You have poles indicated by the blue x's. And now the region of convergence, I hope you can see, is created by a circle that bounds the pole that's the furthest away from the origin, and the region of convergence is beyond that pole that's the furthest away from the origin in the z-plane. This is now pattern 1, region of convergence. That's what these lines extending out are supposed to indicate. These are now the region of convergence. That's what this is supposed to be implying. So the region of convergence is out here beyond all of the poles. Is it clear now that the poles are not on the region of convergence? They are outside the region of convergence, although they're interior to the region of convergence. They're not on top of the region of convergence. I'm not sure which way you want me to say it that will be the least confusing. But do you also see that the region of convergence, in fact, if I said, oh, here is a point in the complex z-plane, and I'm going to let that point go off to infinity. Maybe I should put it in the cloud since everything's in the cloud. That's the point going off to infinity. Do you see now that the region of convergence here is unbounded? It's not bounded by a box or a circle at the external perimeter because it's going off to infinity. It's unbounded. Yes?
So a system can have an unbounded RC but be a bounded system?
So the region of convergence can go unbounded, and we haven't said anything yet about where those poles are living. But the time sequence could be bounded, even though the region of convergence is going off to infinity. It's unbounded. That's the first paragraph that I tried to make clear, is that those concepts are independent, or those two conditions are independent, but they are connected, as we will soon see. But now, unbounded region of convergence really just says that the region of convergence contains, or includes, maybe I should say includes, infinity. Pattern 1, then, if you needed to somehow describe it verbally, you might say, oh, it's an unbounded region of convergence with a central void. And that void is a very specific geometric shape. You take a drill and you drill a hole where the drill bit is large enough to include all of the poles that are interior to the region of convergence. That's the void that you're creating in the region of convergence. Now I'm trying to write this many different ways. One description of this is the region of convergence lies beyond all poles. Does that make sense for this region of convergence? Pattern 1. The region of convergence lies beyond all poles. The blue X's are the poles. The region of convergence lies beyond that. Another way of saying that, let me say that this is now description B for pattern 1. All poles are interior to the region of convergence. Two different ways of trying to say the exact same thing, trying to describe exactly the same region of convergence. Just whichever one resonates with you or you like, as long as it's clear what we mean by the region of convergence. Now what we want to do is figure out what that implies about the time sequence relative to this region of convergence. What do we now know? We now know that this particular capital X of z is supposed to be a finite number. And we know what the region of convergence is. We know it goes unbounded. We now have a particular value of z that we can inject into this expression and test to see, are all of these terms present in that infinite series. If you plug in infinity where z is, what does that mean or impose on some of these sequence values, which are represented by x at minus 2, x at minus 1, x of 0. So we have x of 1, z to the minus 1, plus x of 2, z to the minus 2. We plug in one of those particular values in the region of convergence. Let's just let it go off to infinity. We plug that in, and now we see that we have infinity times x of minus 1. And we know this sum has to be bounded. What does that tell us about the sequence value x at time n equal minus 1? This one has to be 0, doesn't it? Otherwise, that sum would go unbounded. It wouldn't be finite. If we let z be in the region of convergence, which in this pattern 1, one of those values was when z went to infinity. What does that say about x at minus 2? Well, z going to infinity, z squared is getting even bigger. That means that one has to not be there. And do you see that all of those negative indices time sequence values have to not exist? They have to be 0. The other terms are well behaved when z goes to infinity, because you're dividing by a z or a power of z, and those are well behaved. That says then we can now introduce some new terminology. We can say x of n is causal. Or we could also say x of n, the sequence, is equal to 0 for all n negative. Same statement. X of n being causal means that x can only be non-negative or non-zero when little n is non-negative. That's the implication of pattern 1's region of convergence. And we haven't said anything yet about these values for x of 0, x of 1, etc. x of 2. But here could be a picture of what we have now in existence. Everything over here is 0. Everything that's to the right can be non-negative. Are we warm and fuzzy on pattern 1? Pattern 2. Let's do the opposite. Pattern 2 now says that we have these poles at different locations, and now we're finding the one that's the closest to the origin, and we're drawing a circle, a disk, inside that pole, and we're shading that region and saying, here's our second pattern for the region of convergence. It's now a disk. Here, the region of convergence is a bounded disk. We have finite poles, and now that disk is inside the smallest of those poles. So our region of convergence is inside all of our poles, since it's inside the one that has the smallest radius. And the region of convergence is just a disk in shape. So the region of convergence is a bounded disk. What are some ways that we could word that? We could say region of convergence lies inside all poles. That's one way of saying it. Another way for pattern 2, description B might say that all poles are exterior to the region of convergence. They are outside the region of convergence, or they lie beyond the region of convergence. If this is now our region of convergence, can we say anything about when or if any of these sequence values or sequence terms must be turned off or zero? If we look at this, and last time we looked at a particular z, and that z was when z was going off to infinity. Here, do you see a particular z value that might be important or critical? 0. So now we're looking at that point and saying, oh, well, that belongs to the region of convergence. Does that allow us to draw any conclusions relative to terms here in this z transform expression if we know that the sum has to be bounded? So now we know that x at time 1, at x at n equal 1, is scaled by 1 over z, and if z was 0, that would go unbounded. So this piece has to be not there. That forces x1 to be 0. And I think you can see where this is going. x2 has to be 0. And so do all of these dots. Yes. So that's when z is equal to 0. Because that was an extreme, that was inside the region. So the region of convergence has to be true for all values of z in that for this x of z to be defined, capital X of z to be defined. And we've now found that, oh, in this particular case, the positive values of little n have to all be 0. Or the implication then is that little x of n is the opposite of causal, or it's non-causal. This is now non-causal, meaning it's non-zero for values of n that are negative. Or you could say x of n is equal to 0 for all n bigger than 0. And now we could draw this picture. And this could just keep going and going. Or if you don't like the ellipses on the negative side, you could put them up here. But on the positive side of n, those time indexed values have to be 0. That's pattern 2. So we found pattern 1, pattern 2. Now we get this, shouldn't call it a donut, especially at this time, but it's beyond breakfast, right? We can't have donuts at this time. It could be a bagel, I guess. Something annular. We now have an annular region of convergence. It's now, where are the poles? Do you see any poles lying on top of this shaded region? No. So the region of convergence cannot contain any poles, but you could see that you could define a lot of interesting or different annular regions depending on where it was relative to the poles. But here I've simply picked an annular region to try to emphasize that it's now some poles are inside the region of convergence, not on the region of convergence. Some are beyond the region of convergence. Now, how am I going to say this? The region of convergence is annular or donut-shaped, and the first description is that ROC is annular or donut-shaped, or another way of describing that might be to say some poles are interior to the region of convergence, and some poles are exterior. What can we say now about some of those sequence values for negative values of little n or positive values of little n? Can we make any claim on those, or are any of those forced to be equal to 0 like in the previous patterns?
Would it be that, for example, x2 and x negative 2 would not be included?
So now can it be possible that x of 2, because now this sum is going off to infinity. I have x3 z to the minus 3, x4 z to the minus 4, and I also have x minus 3, z to the 3, etc. The comment was, or the remark was, is it possible that x of minus 2 and x of 2 are 0? They could be, but do they have to be? They're not forced to be, are they? Now, z equal to 0 is not a part of the region of convergence, and neither is infinity. We don't have those two extreme values of z, which means that this particular series could be well behaved for any kind of time domain waveform on either side of n equals 0. So the implication is x of n is a two-sided, contrasted with previously, those were one-sided sequences, either right-sided or left-sided. X of n is a two-sided sequence, or x of n is non-zero for n greater than or equal to 0, or can be. X of n can be, maybe that's what I should say, x of n can be non-zero for n greater than or equal to 0 and n less than 0. And a picture of that could be this. where now our sequence is going off. And I didn't yet say anything about the bounded behavior of that sequence, whether it was unbounded or bounded in the time domain, based on these region of convergence patterns. There's now two variations on these, and I'll call them modified pattern 1. Here's pattern 1, except now what I want to do is not allow that region to go unbounded. I do not want this to contain infinity or include infinity. So now I do want to make it clear that the region of convergence does not include z going off to infinity. So if the region of convergence doesn't contain infinity, how would we write that? Or could we express that in an inequality way? Before, we could have said, oh, R1 is less than z, the magnitude of z. But now what do we have to do? In pattern 1, without the variation, we could have said z is bigger than some radius, R1. Now we need to say that, oh, that can't go off to infinity, so that's less than infinity. So the region of convergence, in this case, the ROC remains bounded. That allows us actually to say that x1 of n for pattern 1 is not just causal, it could be right-sided. It could be more general than a causal waveform. x1 of n is right-sided, and not just causal. By that, I'm meaning you could have a finite number of terms on the negative side of n equals 0. That's what I'm meaning by right-sided. Here's the right side. And below, or less than minus m, x1 of n has all 0 values. They're the n that are less than minus m, where minus m is negative. So maybe minus capital M is minus 12. Those finite terms could be there, could be present, because now z is not going off to infinity. The region of convergence remains bounded. It's now no longer unbounded. It has this box around it, where the box is saying you stay away from infinity. Modified pattern 2. How can we modify this pattern? Now, if you've already printed out the notes, you know, or if I just happen to scroll up just a little, what if the region of convergence doesn't include z equals 0? And now you pick your favorite way to make that drawn, but let's just say now we have excluded the origin. We have this disk with z equal to 0 removed from it. That's now our region of convergence. And that's modified pattern number 2, or a variation on pattern number 2. Or now we're saying what? Now we could say that, how would we write this in terms of an inequality expression in terms of the magnitude of z? Before, we could have said, oh, z is less than some, in this drawing, r sub 2. That's pattern 2. The modification says we need to also bound z away from 0. Now we have a left-hand piece to that, and we now say, what if the region of convergence doesn't include z equals 0? That is, what if we could write it this way? That's now a way of describing the modified region of convergence pattern 2. Hopefully now you can see that that means that if the time sequence we label as x sub 2 of little n, that's now left-sided, which is a generalization of non-causal or anti-causal. So this is not just anti-causal. Where our picture now looks like this. Here's our left-sided picture. Or x sub 2 of n is now 0 for all the n bigger than capital N. But we could still have capital N being some finite value. We now have a finite number of sequence terms that are non-zero. In order to have that, our region of convergence has to be modified slightly, or we have to take out z equal to 0. What are our region of convergences? Patterns. We could describe them all by food items except maybe the first one. Help me with that. Is that a tortilla with the center cut out? But that tortilla is big, isn't it? It's unbounded. The next one's a pancake. Pattern 2. The next one is a donut. But do you see, really, they could all be annular in a way? It's just that maybe that pattern 2 is annular in that the middle's kind of gone. It collapsed in itself. The other one is the middle's still there, but the outside just went really, really big. But let's just call them what? The z-plane with the middle, a void, central void removed, or a central void, a disk removed. We have a disk, that's pattern 2, and then we have an annular pattern. Those are our 3 patterns, and then we have variations on pattern 1 and pattern 2. Variation on pattern 1, we says don't go to infinity. Variation on pattern 2, don't include the origin. Let's look at some examples. Or before we do that, let me play along with my cue cards. Yes, question?
So is modified pattern 2 bounded still?
So now modified pattern 2, is it still bounded? What are you meaning by bounded?
So we pause.
So the disk is bounded. The disk is now bounded by the smallest pole in our z-plane. We have all of these poles. We find the one closest to the origin, and we say that's now the one that's bounding our disk. Then we modify it ever so slightly by just taking a pin and putting a hole at the origin and removing that value of z. But it's still a bounded disk with the origin removed. That's modified pattern 2. Did that answer your question? So I'm not saying anything about where those poles are located or the sequence, time sequence in the time domain. Here I'm saying the region of convergence is bounded. Make sure that you are clear that that doesn't necessarily mean anything about what's happening to the time sequence, whether it's bounded or not, and we'll see that in a minute. Yes?
I'm kind of just thinking about this off the top of my head, but why don't we have an inverted pattern 3 where, like,
So now how can we have an inverted pattern 3? Can we? So now the region of convergence has to be connected. So the question was, can we have sort of a disconnected set of a region of convergence? That's, I think, what you were getting at. That's not allowed. Our region of convergence needs to be connected, meaning we need to be able to walk to any point in that region of convergence without having to jump across a void or some missing part of the z-plane. Does that help? So your region of convergence is a connected region in the z-plane. What if x sub 3 has a finite duration? This was one of your homework problems, really, kind of in a region of convergence sense. Now I'm saying x sub 3 of n is not 0 only for a finite value or a finite set of time indices n, from minus capital N up to capital N. Or x sub 3 of n is 0 for n less than minus n and little n greater than capital N, Nevada. So negative Michigan, positive Nevada, if I'm not enunciating properly with M and N. Then the region of convergence can include all of the complex plane except, we know the region of convergence doesn't go off to infinity if we have some non-negative sequence terms that are to the left of the origin. Otherwise, the region of convergence, otherwise the sequence, the series would blow up because we would have z terms in our finite series with z and z squared, z cubed. We can't let z go to infinity. So the region of convergence for a finite duration sequence is the entire complex plane except maybe it doesn't go off to infinity and or maybe it doesn't include the origin. If we had non-zero terms for positive indices, then it can't include z equal to 0. Because the positive terms in that series, finite series, would lead to x of 1 over z plus x of 2 over z squared. And we can't let z go to 0 or those terms would go unbounded. Questions on that? So when you have a finite duration time sequence, your region of convergence could be the entire complex plane except for one or both of these extreme conditions. So if your sequence is straddling both, a little positive, a little negative, you can't have the origin and infinity in your region of convergence. But that's a nice sized donut, isn't it? Just have a little pin out of the center, and boy, is it big. Okay? But if you have a sequence that's only defined on the right or the left of n equals 0, then you would have one or the other of these particular values of z not included in your region of convergence. Let's look at some examples. Suppose that x sub 4 of n is 5 delta of n. This is now our Kronecker delta. This is a value of 1 at n equal, or when this delta is equal to 1 when its argument is equal to 0. Hopefully you can see that x sub 4 of n is in fact that sequence of numbers in the time domain plot. It's 5 at n equals 0. Delta of n minus 1 is on when n minus 1 is 0, or when n is equal to 1. So now we have 1 times 6. That gives us a value of 6 at n equal 1. At little n equal to 2, we're at 7, using the same logic. What's the z transform? Well, by definition, it's this infinite sum. But now, little x sub 4 of n only has 3 non-zero values. We know that it's x at time 0 times z to the minus 0, so that's x of 0 times 1, that's 5, plus 6 z to the minus 1 plus 7 z to the minus 2. And we could write that as 5 plus 6 over z plus 7 over z squared. Or we could write that all over a common denominator of z squared. To be something like that. And what's my region of convergence? What values of z allow this sum of 3 terms to be bounded or finite? All values except the origin, right? All values except when z is equal to 0. So here our region of convergence, we could say, is all complex numbers minus the origin. Or we could say something like that, couldn't we? Region of convergence is the magnitude of z is bigger than 0. Is that okay for our region of convergence and for our z transform? What about x sub 5 of n? Hopefully you can see how that picture pattern in the time domain is consistent with the expression. It has a value of 4 when the argument of that delta is equal to 0 that scales 4, and that's when n is equal to minus 1. It has a value of minus 7 when n is equal to minus 2, and it has a value of minus 1 when n is equal to minus 3. What's the z transform? You could, if you wanted to, you could say, well, I don't know, it's something, it's this. So now you're in an interview and she goes, what's the z transform? And you go, I remember the definition. And then that helps you figure it out. And hopefully they won't say, write it down immediately. You can say, well, let me just think it through here. Now you know that little n is only going over 3 values, and they're negative. We now have x at minus 1, z to the minus minus 1, or that was in fact 4, z to the minus minus 1 is 4z. Then we have minus 7, z to the minus minus 2, or z squared, and then minus 1, z to the minus minus 3. What's the fifth rock? Region of convergence now I'm calling rock. Sub 5 for the region of convergence number 5. What values of z allow this to remain bounded? Z less than 0. Z equal to 10 is okay, isn't it? Z equal to 1 is okay. Z equal to 0 is okay. We just need it to be less than infinity, don't we? So now this is the entire complex plane without infinity. Is the region of convergence unbounded? No, the region of convergence is bounded because it doesn't include infinity. It's not going unbounded. So ROC sub 5, we could say, is z. The magnitude of z just needs to remain below infinity. Or ROC 5 doesn't include infinity, and we've also said that ROC needs to remain bounded. This is so fun. Let's just keep counting. Here's x sub 6. X sub 6 of n is 2 delta n plus 1 minus 4 delta n minus 1. This is now two-sided, but it's finite. What's the z transform of this one look like? Two gets scaled by what power of z? Z to the minus 1 raised to the minus 1, or that's z. And then we have a minus 4, z to the minus 1. Or we could say that this is now z, and this is, did I do that right? This is now a rational expression for x sub 6 of z, and what values of z allow this to remain bounded or give us a finite value? Now our region of convergence needs to be bounded. It needs to be bigger than the origin and less than infinity. It's big, but it doesn't include infinity and it doesn't include the origin. That's our region of convergence. Yes?
If we're given like the example from 1, if we're just given that Z transform, how do we know that we shouldn't include infinity in it?
So now the question is, if we're given a particular Z transform expression, if you aren't told what the sequence looks like, or if you're not told the region of convergence, it could be different possibilities. So you can't say for certain unless somebody gives you that. So they need to tell you what the region of convergence is along with that transform, or they need to show you here's the sequence and here's the Z transform. Now you can derive or tell them what the region of convergence is. But they can't just hand you a transform expression and say, good luck. Now you're going, wait a minute. This could be associated with a left-sided, a right-sided. It could be two-sided. What is it? You don't know. You can't. So you'll say, I need more information before I can tell you what this Z transform corresponds to in the time domain. That's why we need the region of convergence to determine a unique sequence in the time domain, to determine a unique x sub 6 of little n, to determine a unique x sub 5 of n. We need to be told, or in this case, we were given the sequence, we can determine what the region of convergence is. But if somebody just immediately hands you a transform expression, they're not giving you enough information to be able to go back into the time domain. They need to tell you, in addition to that expression, that capital X of Z, they have to provide you with a region of convergence. If they do not, then you could come up with all sorts of different scenarios for the time domain sequence that could lead to that same Z transform expression, which is where we're going now. So that was a great lead-in question to what we want to do. Why do we need the region of convergence? To allow us to determine a unique time domain expression for a given transform expression. But to finish this up, let me just say now that region of convergence wow. Somebody is, I hope that wasn't my phone. Region of convergence 6 doesn't include somebody asked Siri a question, or maybe I did, unknowingly. The region of convergence 6 doesn't include z equals 0, and it doesn't include z going off to infinity. The previous question now gives us a reason for this next segment of the material. Let's examine two cases of a Z transform and the region of convergence. And what we will show is that we can have a similar transform expression and two completely different time domain sequences. So here's case 1. Suppose now that somebody says, I want you to find the Z transform, and this question could be on exam 1, but as I said before, exam 1 really is concerned with positive or non-negative values of little n. But now we've grown beyond that. We have our big boy pants on. We now can go beyond. We're now beyond just considering n non-negative. Okay? So let's now find the Z transform for this. This is 1/2 to the n for n less than 0. And if you just kind of want to get a handle on this, x sub 1 at minus 1 is 2, since we're inverting 1/2. Then x sub 1 at minus 2 is the square of that. It's 4. So now, what's the time behavior of that x sub 1 of n? How is it behaving? As n marches off to the left, as n gets more and more negative, what's happening to the value of x sub 1 of those values of n? It's exponentially going unbounded, isn't it? It's going unbounded. Does it have a z transform? Let's see. Here is what we have. We could write this now as x1 of n. We could say x of n, u to the minus n to the minus 1. That's only turning on these coefficients for negative values of little n. We put that switch in there if we wanted to. We wouldn't have to if we have it written in this form. But now, to keep the knowledge or the fact that the argument is only going to be assuming non-negative values for n negative, I'm putting that u of minus n minus 1 in there. How do we do this? This is now the sum from n equal minus infinity to minus 1. Those are the only ones that are associated with non-negative values of the sequence. They now are 1/2 to the n. That's what we were given. These are 1/2 to the n for negative values of n, and this is z to the minus n. And now we can combine that however you want. We could say this is now equal to summation from n equal minus infinity to minus 1. We could say this is 2 to the minus 1 to the n if we wanted to. Or this is now 2 to the minus n times z to the minus n. So that we could now write that as this sum from minus infinity to minus 1 of 2z to the minus n. And now, oh, that's kind of confusing. We have negative powers, we have negative indices. We could do a change of variable if we wanted to, but in this particular, well, let's do that. So now let's say, let's change n or minus n and let it equal L. So that capital X sub 1 of z is now this sum from L equal 1 to infinity. L now is going from 1 to infinity. That's maybe more comforting. And what do we have here? We didn't change the argument, but now minus n we set equal to L. What's our common ratio? This is a geometric series, isn't it? That changes in each of those terms in the series by this factor of 2z. We now have a geometric series where 2z is our common ratio. And we know also that this will converge as long as what's true. When will this tail gets smaller and smaller so that the sum of all of that tail gives us a finite value. As long as that 2z, as long as that common ratio is less than 1. So this will now converge as long as 2z, the magnitude of that, is less than 1. Or now, what's my region of convergence? What values of z cause this capital X1 of z to produce a finite sum? So now we can divide out the magnitude of z if we want, or maybe divide by 2 on both sides. That's cleaner. So now we have that. This is now our region of convergence. And if we want to find the closed form expression for capital X1 of z, we could start doing that like we'd done before. Let's just call this W for now, so that I don't have to write so much. I now have capital X1 of z. Now I don't start with 1, do I? Since L is equal to 1, I start with W plus W squared plus W cubed, etc. Now what could I multiply capital X sub 1 of z and still end up with the same tail shape? Or what do I want to compare this to? Probably don't want to multiply it by W. I could, I guess, but it's cleaner to multiply by the inverse of W. So now let me say this I'm going to compare with that, which I scale all of those terms on the right by W inverse, and I end up with 1 plus W squared plus W cubed. My tail looks the same, or the tail on these two expressions. I don't have a tail, if you online students were wondering. So, what do we have? All of these pieces are common to both the top and the bottom expression. If I now take their difference, I have 1 minus W inverse times X1 of z equaling what? Now I've subtracted the second from the first, so I have a minus 1 on the right-hand side. Or capital X1 of z is now minus 1 over 1 minus W inverse. Or if I multiply that by W, I end up with minus W over W minus 1. And I didn't have it in terms of W. I wanted it in terms of z. This is the z transform. X1 of z is now, W was 2z, wasn't it? Not 2b, or we would be in another class. 2b or not 2. Sorry. It's 2z. Rhymes with b. Okay, we're getting close. Same idea. We could maybe go into limericks and rhymes. Anyway, this is now minus 2z over 2z minus 1. Factoring out a 2, we could have minus z over z minus 1/2. And when was this going to be valid, or when did that have a finite value? When the magnitude of z was less than 1/2. Can you now draw the region of convergence? First, I have a complex z-plane, and I've shown you the unit circle. Now, can you draw the pole zero diagram on that z-plane? Where are my zeros, finite zeros, and where are my poles? I have a pole at, what color do I want to make these? I have a pole right, I'm sorry, I have a 0 right at the origin, do I not? Z equal to 0 will cause x sub 1 of z to vanish. Where's my pole? That's the value of z that causes the denominator to equal 0. That's 1/2. What's my region of convergence? Everything inside. That's supposed to be a circle. Doesn't look like it's symmetric about the origin, but you can make yours symmetric. That's now the region of convergence. Where did the 0 come from? So I'm looking for finite values of z. Zeros are defined to be really the values of z that cause that numerator polynomial to vanish. Those are then, for this one, a finite value of z is too easy to see. It's actually when the numerator is 0, which is z equals 0. That's why I have a 0, or a open circle. That's my 0 in the z-plane. But it's inside the ROC. I didn't say anything about zeros in the ROC. What did I say? I said poles can't be on the ROC. I didn't say anything about zeros. Yes, that's a valid question. But now that pole is just bounding the region of convergence. What comments can we make or observations can we make relative to what we've just concluded with this first case? What was the time response behavior of x, was it x sub 1? Little x sub 1 of n, how did that behave in the time domain? Do you remember? What was happening when little n went off to negative infinity? It was going unbounded, wasn't it? That particular time domain response is unbounded. Maybe I should say observations how does the unit circle compare to the region of convergence? Is the unit circle on top of the region of convergence? Is it contained within the region of convergence? No. And our sequence, time sequence, was unbounded. That's a big connection to make. The unit circle is not contained in the region of convergence. So the second observation is the unit circle doesn't lie on top of the region of convergence. And in fact, those two comments are the connection we want to make. If the unit circle is contained within our region of convergence, do you see that you could have had, let's say that pole was at 2 instead of at 1/2. Then what would our region of convergence look like? And what would our time sequence look like? Now we have 2 to the minus 1, 2 to the minus 2, 2 to the minus 3. That's collapsing, isn't it? And what would our region of convergence have done? It would have contained that unit circle. What if, now let's think of some other, we have just a minute to sort of be thinking. What if we looked at pattern number 1? What if now I had a pole at 1/2 and my region of convergence was outside of that pole? Pattern 1 with a pole at 1/2. Does the unit circle, is it contained or on top of the region of convergence? It's contained or it's on top. And what's 1/2 to the 1? 1/2 squared, 1/2 cubed. That's bounded, isn't it? See the connection? If the region of convergence contains the unit circle, we're going to have a bounded time domain response. What if I had two poles, one at 1/2 and one at 2, and I had an annular region of convergence? I would have a bounded time domain sequence that's two-sided. One would be going 1/2, 1/2 squared, 1/2 cubed, etc. Another one would be 2 to the -1, 2 to the -2, etc. on the left side. Those would be bounded. But my region of convergence would contain the unit circle. That's the connection we will pick up on Monday. We finished this session, but then we will soon begin our second half of today's marathon.